If you roll a snowball down a hill, it picks up snow. As it gets bigger, its surface area expands, allowing it to collect more snow with every rotation. This is the process of compound interest. You earn interest on your initial deposit, and then you earn interest on that interest. This graph compares two different ways money grows. The flat orange line is simple interest, adding a fixed amount every year. The blue curve is compounding interest, which grows at an exponential rate because the total balance increases with every period. We calculate that growth using this formula. We have the final amount, Vn. We have the starting principal, V0. We have the interest rate, R. And we have the number of compounding periods, N. The engine of the equation is inside the parentheses, 1 plus the rate over 100 to the power of n. This is the growth factor, the specific multiplier that determines how large the final total becomes. Understanding the inputs of this equation is the first step toward predicting how fast a balance will grow over time. Let's look at a baseline scenario, investing $4,000 for 10 years at an 8% annual rate. To simplify the growth factor, we divide the 8% rate by 100 to get 0.08. Adding the 1 gives us a growth factor of 1.08. Raising 1.08 to the 10th power and multiplying by the principal gives us $8,635.70. To find the pure interest earned, we subtract our original $4,000 investment. While annual compounding is a direct calculation, most financial systems operate on much more frequent timelines. Banks often compound interest quarterly or monthly. When this happens, we have to adjust our variables to avoid inaccurate results. First, adjust the periods n by multiplying the years by the compounding frequency, like by 4 for a quarterly account. Second, adjust the rate, r. Divide the annual rate by that same frequency to find the interest per period. For 12 years at 6% compounded quarterly, we multiply 12 by 4 to get 48 periods. Then we divide the 6% rate by 4 to get a quarterly rate of 1.5%. Plugging these into the formula, $6,000 times 1.015 to the 48th power results in a final balance of $15,522.42. Forgetting to adjust both the timeline and the rate is the most common reason for errors in compound interest math. Now try a different challenge. Find the starting principal needed to reach exactly $5,000 in 5 years, compounding monthly at a 6% annual rate. Pause the video now. Adjust your n and r variables for a monthly schedule and set up the equation to solve for the principal. Working the equation backward helps clarify how each variable interacts with the final goal. To solve this, we multiply 5 years by 12 to get 60 months. Then we divide the 6% rate by 12 to get a monthly rate of 0.5%. We set the final goal of $5,000 equal to the principal times 1.005 to the 60th power. Dividing 5,000 by that growth factor shows we need a starting principal of $3,706.86. These 3 steps, using the core formula, isolating the interest, and adjusting for frequency, allow you to model almost any compounding scenario. By applying these adjustments, you can accurately determine the specific inputs required to reach any financial milestone.